Hello there, and welcome to the Deep Sleep Discoveries channel. If you're someone who likes to unwind by thinking about distant worlds, the quiet mechanics of orbits, and the gentle mystery of planets turning through space, you're in the right place. Tonight, we're embarking on a journey through 100 planetary facts, drifting from our own solar system outward to the strange and beautiful exoplanets that circle distant stars. We'll visit worlds of ice and fire, planets that defy explanation, and moons that hold secrets beneath their frozen shells. Some of what you'll hear might seem impossible, but all of it is real, drawn from the careful observations of astronomers and the data returned by our spacecraft. If you enjoy these sleepy journeys through science, you're welcome to like and subscribe. It helps others find their way here too. But for now, there's nothing you need to do. Just get comfortable, let your body settle, let your breath slow, let your thoughts begin to wander like light across the surface of a distant planet, and let's begin. Mercury has no atmosphere to retain heat, so temperatures swing about 1,100 degrees Fahrenheit between day and night. Imagine standing on a world where the sun beats down with relentless intensity, heating the rocky surface to over 800 degrees during the day. But when night falls, there's no blanket of air to hold that warmth. The heat radiates back into space almost immediately, and temperatures plummet to nearly negative 300 degrees. It's one of the most extreme temperature ranges of any planet in our solar system. This happens because Mercury lacks the protective atmospheric layer that Earth enjoys, the invisible cushion that moderates our climate and keeps us from freezing or burning. On Mercury, there's nothing between the surface and the void. The planet is exposed, raw, and vulnerable to the whims of solar radiation. During the long Mercurian day, the ground becomes hot enough to melt lead. During the night, it's colder than the coldest winter on Earth. It's a world of contrasts, a place where survival would require constant adaptation. And this lack of atmosphere leads to another curious feature of Mercury's behavior in space. Mercury completes 3 rotations for every 2 orbits around the Sun. This unusual rhythm is called a 3-to-2 spin-orbit resonance, and it means that Mercury's day and year are linked in a way that's different from any other planet. If you were standing on Mercury's surface, you'd experience something strange. The sun would rise, move slowly across the sky, then sometimes appear to stop, reverse direction briefly, and continue on its path before setting. This happens because of the interplay between Mercury's rotation and its elliptical orbit. As the planet speeds up and slows down in its journey around the Sun, its rotation can't quite keep pace in a uniform way. The result is a sky that behaves unlike anything we see from Earth. A single day on Mercury, from one sunrise to the next, lasts 176 Earth days. That's 2 full Mercurian years. It's a slow, strange waltz between the planet and its star, a gravitational dance that has settled into this precise mathematical relationship over billions of years. And while Mercury moves in this peculiar rhythm, our neighbouring planet Venus has an even stranger rotation. Venus rotates backwards compared to most planets in our solar system. While Earth, Mars, Jupiter, and most other planets spin counterclockwise when viewed from above the Sun's North Pole, Venus spins clockwise. This retrograde rotation is rare and still not fully understood. Scientists believe it may have been caused by a massive collision early in Venus's history, an impact so powerful it knocked the planet's spin into reverse. Or perhaps it was the result of gravitational tides from the Sun acting on Venus's thick atmosphere over billions of years, gradually slowing and then reversing its rotation. Whatever the cause, the result is a planet that turns against the grain. If you could stand on Venus's surface and survive the crushing pressure and searing heat, you'd see the sun rise in the west and set in the east. It's a backwards world in more ways than one, a place where even the most fundamental motions are inverted. This retrograde spin also affects how long a day lasts on Venus, creating one of the most peculiar day-night cycles in the solar system. A day on Venus, which lasts 243 Earth days, is longer than its year, which lasts only 225 Earth days. Let that settle for a moment. It takes Venus less time to complete a full orbit around the Sun than it does to rotate once on its axis. This means that if you were somehow able to stand on Venus's surface, you'd experience a year passing before a single day-night cycle completed. The sun would creep across the sky with agonizing slowness, taking months to move from horizon to horizon. This strange relationship exists because Venus rotates so slowly, more slowly than any other planet. Combined with its retrograde spin, it creates a world where time seems to move differently, where the usual markers of days and years blur into one long, drawn-out experience. The thick atmosphere of Venus, which contributes to its extreme conditions, also plays a role in this slow rotation, creating friction and drag that may have further slowed the planet's spin over time. And speaking of Venus's atmosphere, it's responsible for making this planet the hottest in our solar system. Venus is the hottest planet in our solar system, despite Mercury being closer to the Sun. Surface temperatures on Venus reach around 900 degrees Fahrenheit, hot enough to melt lead and far hotter than Mercury ever gets, even at its sun-facing side. The reason for this extreme heat isn't proximity to the Sun, it's Venus's atmosphere. The planet is wrapped in a thick blanket of carbon dioxide, with clouds of sulfuric acid floating in the upper layers. This creates a runaway greenhouse effect, where heat from the sun gets trapped and can't escape back into space. The atmosphere is so dense that the pressure at the surface is about 90 times greater than Earth's, equivalent to being a kilometre deep in the ocean. Heat builds and builds, with no release, no cooling wind, no relief. The result is a surface hot enough to glow faintly in the darkness, a world where metal softens and the air itself would crush and burn you simultaneously. It's a cautionary tale of what can happen when a planet's atmosphere becomes imbalanced, and this extreme greenhouse effect is powered by the very composition of Venus's thick air. Venus's thick atmosphere creates a runaway greenhouse effect with temperatures around 900 degrees Fahrenheit. This atmospheric composition is about 96% carbon dioxide, with nitrogen and trace amounts of other gases making up the rest. The carbon dioxide acts like a heat-trapping blanket, allowing sunlight to pass through to the surface but preventing infrared radiation from escaping back into space. As the surface heats up, it radiates heat, but that heat is absorbed by the atmosphere and re-radiated back down, creating a feedback loop that continually raises the temperature. This is what scientists call a runaway greenhouse effect, where the warming becomes self-reinforcing and spirals out of control. Venus may have once had liquid water on its surface, oceans that evaporated as the sun grew brighter over billions of years. That water vapor, itself a greenhouse gas, would have amplified the warming, leading to more evaporation, more warming, until the oceans were gone and the planet was left as the scorching furnace we see today. It's a sobering reminder of how delicate planetary climates can be. And while Venus shows us the extremes of heat, our next neighbour shows us a different kind of beauty. Mars appears red because its surface is covered in iron oxide, commonly known as rust. The planet's distinctive rusty hue has captured human imagination for millennia, long before we understood what caused it. The iron in Mars's soil oxidized over billions of years, likely due to water and oxygen in the planet's ancient past. This rust coats the rocks, dust, and regolith, giving the entire planet a reddish tint that's visible even from Earth with the naked eye. When dust storms sweep across Mars, and they can be planet-wide, they lift this fine rusty dust into the atmosphere, sometimes obscuring the surface entirely and deepening the red color of the sky. The Martian sky itself isn't blue like Earth's. During the day, it's a butterscotch or peachy hue, with the dust scattering light in different ways than our nitrogen-oxygen atmosphere. At sunset, however, the sky around the sun glows blue, the opposite of Earth's red sunsets. It's a world painted in rust, a cold desert where iron has slowly surrendered to oxygen, leaving behind the color of oxidation and time. And beneath this rusty surface lies evidence of Mars's more dramatic geological past. Mars has the largest volcano in the solar system, Olympus Mons, nearly 3 times the height of Mount Everest. This shield volcano rises about 13.6 miles above the Martian surface, so tall that its peak would pierce through much of Earth's atmosphere if it were transplanted here. But Olympus Mons isn't just tall, it's also enormous in diameter, stretching about 370 miles across, roughly the size of the state of Arizona. The volcano's slopes are gentle, rising gradually from the surrounding plains, but at its base are cliffs up to 6 miles high where the edge of the volcanic structure drops away sharply. Olympus Mons formed over millions of years as lava flowed repeatedly from the same hotspot, building up layer upon layer. Unlike Earth, where tectonic plates move and shift volcanoes away from their magma sources, Mars has no plate tectonics. The crust stayed stationary over the hotspot, allowing the volcano to grow to immense proportions. It's likely extinct now, dormant for tens of millions of years, a silent monument to Mars's volcanic past. And Olympus Mons isn't the only fascinating feature of Mars. The planet also has 2 small, mysterious moons. Mars has 2 small, irregularly shaped moons, Phobos and Deimos. These moons are tiny compared to Earth's moon. Phobos, the larger of the 2, is only about 14 miles across at its widest point, while Deimos is even smaller at just 7.5 miles. Both are dark, rocky, and heavily cratered, resembling asteroids more than traditional moons. In fact, many scientists believe they are captured asteroids, pulled into orbit around Mars long ago by the planet's gravity. Phobos orbits extremely close to Mars, closer than any other moon orbits its planet in the solar system. It completes an orbit in just 7.6 hours, meaning it rises and sets twice in a single Martian day. From the surface of Mars, Phobos would appear to move backwards across the sky compared to the Sun and stars. Deimos, on the other hand, orbits much farther out and takes about 30 hours to complete an orbit, rising in the east and setting in the west like a more traditional moon. These 2 moons are remnants of the early solar system, witnesses to Mars's history, and they continue to orbit faithfully as the red planet turns below. But if Mars's moons are small, Jupiter's presence in the solar system is anything but. Jupiter is so large that 1,300 Earths could fit inside it. This gas giant dominates our solar system, containing more mass than all the other planets combined. Its diameter is about 11 times that of Earth, and its volume is so vast that it's hard to truly comprehend. If Earth were the size of a grape, Jupiter would be the size of a basketball. The planet is made primarily of hydrogen and helium, the same elements that make up the Sun, and in fact, Jupiter is sometimes called a failed star. If it had been about 80 times more massive, it would have had enough pressure and heat at its core to ignite nuclear fusion and become a star itself. Instead, it remained a planet, but one with incredible gravitational influence. Jupiter's gravity has shaped the orbits of asteroids, comets, and other planets. It acts as a cosmic vacuum cleaner, deflecting or capturing objects that might otherwise collide with the inner planets. Its presence has protected Earth from countless impacts over billions of years. And on Jupiter's surface, or rather in its upper atmosphere, storms rage that dwarf anything we experience on Earth. Jupiter's Great Red Spot is a storm that has been raging for at least 400 years. This massive anticyclonic storm is so large that 2 or 3 Earths could fit inside it, though it has been shrinking over the past century and a half. The storm was first observed by astronomers in the 1600s, and it has been continuously monitored ever since. The Great Red Spot rotates counterclockwise, completing a full rotation every 6 days, with wind speeds reaching up to 270 miles per hour at its edges. The reddish colour is thought to come from complex chemical reactions in Jupiter's atmosphere, possibly involving phosphorus or sulfur compounds that are brought up from deeper layers and then altered by ultraviolet light from the Sun. The storm sits in Jupiter's south equatorial belt, a region of the planet known for turbulent weather. What keeps the Great Red Spot going for so long? Scientists believe it's sustained by Jupiter's internal heat and the powerful jet streams that flow around it, feeding it energy and preventing it from dissipating. It's a storm older than nations, older than modern science itself, still swirling in the clouds of a distant giant. And Jupiter's mysteries don't end with its weather. The planet is also accompanied by a vast family of moons. Jupiter has at least 95 confirmed moons. This number keeps growing as our telescopes improve and we discover smaller and smaller satellites orbiting the giant planet. These moons range in size from Ganymede, the largest moon in the solar system, down to tiny irregular rocks just a few kilometers across. Many of Jupiter's smaller moons are likely captured asteroids, pulled into orbit by the planet's immense gravity. The 4 largest moons, Io, Europa, Ganymede and Callisto, are called the Galilean moons because they were discovered by Galileo Galilei in 1610 when he pointed his telescope at Jupiter. These 4 moons are worlds unto themselves, each with unique characteristics. Io is covered in volcanoes. Europa has a subsurface ocean. Ganymede has its own magnetic field. Callisto is heavily cratered and ancient. Together, Jupiter and its moons form a miniature solar system, a complex gravitational dance where each moon influences the others. Some moons orbit in the same direction as Jupiter's rotation, while others orbit backwards, their paths chaotic and unstable. And among all these moons, one stands out as particularly intriguing for the possibility of life. Jupiter's moon. Europa likely has a subsurface ocean containing more water than all of Earth's oceans combined. Beneath Europa's icy crust, which is estimated to be 10 to 15 miles thick, lies a global ocean that could be 40 to 100 miles deep. This ocean is kept liquid by tidal heating. The gravitational pull of Jupiter and the other Galilean moons stretches and compresses Europa as it orbits, generating internal friction and heat. The surface of Europa is crisscrossed with long linear fractures and ridges, giving it a cracked, icy appearance. Some areas show evidence of ice plates that have shifted and rotated, suggesting the crust floats on the liquid water below. There are also features called chaos terrain, where the surface has broken apart and reformed, possibly due to upwelling of warmer ice or even liquid water from below. Scientists believe Europa's ocean could have the right conditions for life. liquid water, energy from tidal heating, and potentially organic molecules delivered by comets or created in the ocean itself. It's one of the most promising places in the solar system to search for extraterrestrial life. And Europa is not the only moon with fascinating features. Saturn's moons and rings present their own wonders. Saturn's rings are made mostly of ice particles, some as small as grains of sand, others as large as mountains. These particles orbit Saturn in a thin, flat disk that extends hundreds of thousands of miles from the planet. The rings are remarkably bright because ice reflects sunlight well, giving Saturn its distinctive, jewel-like appearance. The particles are thought to be remnants of comets, asteroids, or moons that were broken apart by Saturn's gravity or by collisions. Each particle orbits independently, guided by gravity and the subtle influences of Saturn's many moons, which act as shepherds, keeping the rings in their lanes and creating gaps and waves in the structure. The rings are not solid. If you could fly through them, you'd pass through a sparse cloud of tumbling ice chunks, each one following its own path. Some of the larger particles might be house-sized boulders of ice, while the smallest are fine dust. The rings sparkle and shimmer as billions of individual pieces catch the sunlight. And despite their grand appearance, these rings are surprisingly thin. Saturn's rings are only about 30 feet thick in most places, despite being over 175,000 miles wide. This extreme flatness makes the rings one of the most geometrically unusual structures in the solar system. If you were to scale down Saturn's rings to the size of a football field, they would be thinner than a sheet of paper. The thinness is maintained by the gravitational influence of Saturn itself and by the collisions between ring particles, which tend to flatten their orbits over time. Any particle that strays too far above or below the main plane of the rings will eventually collide with other particles and be nudged back into alignment. The rings lie precisely in Saturn's equatorial plane, perpendicular to the planet's axis of rotation, a consequence of how gravity and rotation interact. When viewed edge-on from Earth, the rings can virtually disappear from sight because they're so thin, a phenomenon that occurs roughly every 15 years as Saturn's tilt brings the rings into alignment with our line of sight. Despite their delicate thickness, the rings contain an enormous amount of material, and they contribute to one of Saturn's most remarkable properties. Saturn is the least dense planet. It would float in water if you could find a bathtub large enough. This statement is technically true, though of course finding such a bathtub is impossible. Saturn's average density is about 0.687 grams per cubic centimetre, which is less than the density of water at 1 gram per cubic centimetre. This low density exists because Saturn is composed mostly of hydrogen and helium, the lightest elements in the universe. The planet is essentially a vast ball of gas with a small rocky core deep inside, surrounded by layers of metallic hydrogen under immense pressure, and then the outer atmosphere we can observe. Despite being the second largest planet in the solar system, Saturn's mass is relatively small compared to its volume, which gives it this unusually low density. If you could somehow place Saturn in a cosmic ocean, it would bob on the surface like a giant beach ball, though the interaction between the planet's gases and the water would create all sorts of chaos. It's a reminder of just how different the gas giants are from rocky planets like Earth, worlds without solid surfaces, made mostly of the same stuff as stars. And Saturn's largest moon adds yet another layer of intrigue to this system. Saturn's moon Titan has liquid methane lakes and rivers on its surface. Titan is the only other world in the solar system besides Earth where we've confirmed the presence of stable liquid on the surface. However, instead of water, Titan's lakes are filled with liquid methane and ethane, hydrocarbons that are gases on Earth but liquids in Titan's frigid environment, where surface temperatures hover around -290 degrees Fahrenheit. These lakes are found mostly in Titan's polar regions, with the largest, Kraken Mare, covering an area larger than the Caspian Sea. Titan also has rivers, rainfall and weather systems driven by methane, creating a hydrological cycle similar to Earth's water cycle but based on completely different chemistry. The Moon's thick, hazy atmosphere is rich in nitrogen with traces of methane and other organic molecules. This atmosphere is so dense that it creates a surface pressure 1.5 times that of Earth. If you stood on Titan, you could see liquid methane rain falling from orange skies, pooling in lakes, and flowing through river channels carved into water ice bedrock. It's an alien world and yet hauntingly familiar in its processes. And while Titan offers a different kind of liquid landscape, another planet in our solar system presents a completely different type of strangeness. Uranus rotates on its side, with its axis tilted at 98 degrees. Most planets have relatively small axial tilts. Earth's tilt is 23.5 degrees, which gives us our seasons. But Uranus is tilted so far over that it essentially rolls around the Sun like a ball, with its poles taking turns pointing almost directly at the Sun during its 84-year orbit. This means that each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. The cause of this extreme tilt is still debated, but the leading theory is that Uranus was struck by a massive object, perhaps an Earth-sized protoplanet, early in its history. The collision was violent enough to knock the planet onto its side, but not violent enough to destroy it. As a result, Uranus has the most extreme seasonal variations of any planet. During summer at one pole, the sun never sets. During winter, it never rises. The equatorial regions experience more traditional day-night cycles, but even there, the sun's path across the sky is strange and unfamiliar. This unusual orientation also affects Uranus's magnetic field and its appearance from Earth. Uranus appears blue-green due to methane in its atmosphere. The planet's upper atmosphere contains methane gas, which absorbs red light from the sun and reflects blue and green wavelengths back into space. This gives Uranus its distinctive cyan color, a pale, soft hue that makes it look almost serene in photographs. Beneath the methane layer, the atmosphere is primarily hydrogen and helium, similar to Jupiter and Saturn, but the methane gives Uranus and its neighbor Neptune their characteristic colors. The atmosphere also contains trace amounts of water, ammonia, and other compounds. Unlike Jupiter and Saturn, which have dramatic banded clouds and storms, Uranus appears relatively featureless in visible light. Its weather systems are hidden beneath layers of haze, though infrared observations have revealed clouds and storms moving through the atmosphere. The planet's blandness in visible light is partly due to its distance from the Sun. It receives less energy, so its weather is less vigorous. Still, winds on Uranus can reach speeds of up to 560 miles per hour, especially near the poles. And, like Saturn, Uranus has a ring system, though far less prominent. Uranus has 13 known rings, much fainter than Saturn's. These rings were discovered in 1977 when Uranus passed in front of a distant star, and astronomers noticed the star's light dimmed briefly in several places before and after the planet itself blocked it. This revealed the presence of narrow rings circling the planet. Unlike Saturn's bright, icy rings, Uranus's rings are dark, made of dust and larger particles that reflect very little light. The rings are narrow and widely spaced, with sharp edges, suggesting they may be held in place by small shepherd moons that orbit nearby. The composition of the rings is thought to be mostly dark organic compounds and rock with little ice. Some of the particles may be debris from collisions between moons or from comets that strayed too close to Uranus and were torn apart by its gravity. The rings are difficult to see from Earth, even with large telescopes, but spacecraft like Voyager 2 have captured detailed images of them. They add another layer of complexity to an already unusual planet. And beyond Uranus lies Neptune, the final of our solar system's giant planets. Neptune has the strongest winds in the solar system, reaching 1,200 miles per hour. These supersonic winds whip through Neptune's atmosphere, creating dynamic and violent weather systems despite the planet being the farthest from the Sun and receiving the least solar energy. The winds are driven not primarily by sunlight, but by Neptune's internal heat. The planet radiates more than twice as much energy into space as it receives from the Sun, suggesting it has a significant internal heat source, possibly left over from its formation or generated by the slow gravitational compression of its interior. This internal energy powers massive storms, including the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot, though less permanent. The Great Dark Spot was observed by Voyager 2 in 1989, but had disappeared by the time the Hubble Space Telescope looked for it a few years later, suggesting Neptune's storms come and go more rapidly than Jupiter's. The winds on Neptune blow in the opposite direction to the planet's rotation in some latitudes, creating complex jet streams and weather patterns. And like Uranus, Neptune's beautiful blue colour is a result of its atmospheric chemistry. Neptune appears deep blue due to methane absorption of red light. Methane in Neptune's upper atmosphere absorbs the red and infrared wavelengths of sunlight, reflecting the blue wavelengths back into space. However, Neptune's blue is richer and deeper than Uranus's, even though both planets have similar atmospheric compositions. Scientists believe there may be an additional unknown component in Neptune's atmosphere that enhances the blue colour, though this remains a topic of research. The deep azure hue gives Neptune a striking, almost luminous appearance in images captured by telescopes and spacecraft. Beneath the blue haze, Neptune's atmosphere contains clouds of methane ice and possibly water ice, along with the standard hydrogen and helium found in all gas giants. The planet's appearance is more varied than Uranus's, with bright cloud features, dark spots, and a dynamic atmosphere that changes over time. Neptune's beauty is cold and distant, a frozen giant at the edge of the solar system, still active, still stormy, still full of mystery. And Neptune's discovery itself is a story of mathematical triumph. Neptune was the first planet located through mathematical predictions rather than direct observation. In the 1840s, astronomers noticed that Uranus's orbit didn't quite match the predictions based on Newton's laws of gravity. It was being pulled slightly by something unseen. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where an unknown planet would need to be to cause these orbital irregularities. Le Verrier sent his predictions to astronomer Johann Galle at the Berlin Observatory, who pointed his telescope to the predicted location and found Neptune on his first night of searching in September 1846. It was a stunning confirmation of mathematical theory and Newtonian physics, proof that the laws governing motion and gravity could reveal hidden worlds. Neptune was found not by accident or by scanning the skies, but by reasoning through the gravitational influence it exerted from afar. It was a triumph of human intellect over the vastness of space, and Neptune, like the other giant planets, has moons, including one that is especially unusual. Neptune's moon Triton orbits backwards and is slowly spiraling toward the planet. Triton is the only large moon in the solar system with a retrograde orbit, meaning it orbits in the opposite direction to Neptune's rotation. This suggests Triton didn't form alongside Neptune but was captured from elsewhere, possibly from the Kuiper Belt, the region of icy bodies beyond Neptune. Captured objects often have tilted or retrograde orbits because they weren't part of the original formation process. Triton's retrograde orbit has consequences. Tidal forces between Neptune and Triton are causing the moon to lose orbital energy, and it's gradually spiraling inward. In about 3.6 billion years, Triton will cross Neptune's Roche limit, the distance at which tidal forces will tear it apart, and it will be destroyed, forming a spectacular ring system around Neptune. For now, Triton remains intact, a fascinating world with geysers of nitrogen erupting from its surface, a thin atmosphere, and a landscape of frozen nitrogen and water ice. It's one of the most geologically active moons in the solar system, and speaking of extreme cold, Triton is among the coldest places we know. Triton has surface temperatures around -391 degrees Fahrenheit, making it one of the coldest objects in the solar system. At these temperatures, nitrogen, methane, and carbon monoxide exist as ices on the surface, and Triton's thin atmosphere is primarily nitrogen with traces of methane. Despite the extreme cold, Triton shows signs of recent geological activity. The moon has relatively few impact craters, suggesting its surface has been resurfaced by cryovolcanism, where water or other volatiles erupt from the interior and freeze on the surface, burying older terrain. Voyager 2 observed dark streaks on Triton's surface, thought to be deposits of dark material ejected by geyser-like eruptions. These geysers may be driven by seasonal heating from the sun, even at such great distances, warming the nitrogen ice just enough to cause it to sublimate and burst through the surface. Triton's landscape is alien and strange, a world of frozen plains, ridges, and cantaloupe-like terrain with pits and dimples. It's a reminder that even in the outer reaches of the solar system, worlds remain dynamic. And with Triton, we transition from our solar system's planets to the broader story of how planets form. Planets form from rotating disks of gas and dust around young stars. When a star is born from a collapsing cloud of gas and dust, not all of the material falls directly into the star. Some of it settles into a rotating disk called a protoplanetary disk, spinning around the young star like a cosmic record. Within this disk, particles of dust collide and stick together through static electricity and gentle collisions, gradually building up larger and larger clumps. Over time, these clumps grow into pebbles, then rocks, then boulders, and eventually into planetesimals, objects ranging from kilometers to hundreds of kilometers across. These planetesimals continue to collide and merge, forming protoplanets. In the inner regions of the disk, where temperatures are higher, only materials with high melting points like metals and silicates can remain solid, leading to the formation of rocky planets. Farther out, where it's cooler, ices can condense, allowing for the formation of much larger bodies that can accumulate thick atmospheres of hydrogen and helium, becoming gas giants. This entire process takes tens of millions of years, a relatively short time in cosmic terms, and the location where a planet forms determines much of its character. Rocky planets form closer to stars where it's too hot for gases to condense. In the inner regions of a protoplanetary disk, temperatures are high enough that volatile compounds like water, methane, and ammonia remain gaseous and can't freeze into solid ice. Only materials with high melting points, such as iron, nickel, and silicate minerals, can condense into solid particles. These particles collide and stick together, gradually building up rocky planetesimals and eventually rocky planets like Mercury, Venus, Earth, and Mars. The heat from the young star also creates a strong stellar wind that blows away much of the lighter gas in the inner disk, making it difficult for rocky planets to capture and retain thick hydrogen and helium atmospheres. This is why the inner planets of our solar system are relatively small and dense, composed mostly of rock and metal, with thin atmospheres, or none at all. The process creates worlds with solid surfaces, places where you could, in theory, stand and feel the ground beneath your feet. Meanwhile, in the colder outer reaches of the disk, a different type of planet begins to take shape. Gas giants form farther out where volatile ices can accumulate. Beyond a certain distance from the star, called the frost line or snow line, temperatures drop low enough for water and other volatile compounds to freeze into solid ice. This increases the amount of solid material available to build planets, allowing planetary cores to grow much larger than in the inner disk. Once a core reaches about 10 times the mass of Earth, its gravity becomes strong enough to capture and hold on to large amounts of hydrogen and helium gas from the surrounding disk. This gas rapidly accumulates around the core, forming a thick atmosphere that dwarfs the solid core beneath. The result is a gas giant, a planet like Jupiter or Saturn, with a small rocky or icy core surrounded by thousands of miles of gas. These planets form relatively quickly, within a few million years, before the gas in the protoplanetary disk is blown away by the star's radiation. The outer regions of the disk are also where icy moons and ring systems can form, creating the complex satellite systems we see around the giant planets. And the entire process of planet formation is a gradual, patient accumulation. The process of planet formation takes tens of millions of years. It begins with microscopic dust grains in the protoplanetary disk and ends with fully formed planets, moons, and asteroid belts. In the earliest stages, dust grains stick together through electrostatic forces, forming fluffy aggregates. These aggregates collide and merge, growing slowly at first, then more rapidly as their gravity begins to attract additional material. Within a few 100,000 years, kilometre-sized planetesimals form. These are the building blocks of planets, and they continue to collide, sometimes merging, sometimes shattering, in a chaotic dance of destruction and creation. Over millions of years, a few planetesimals grow dominant, sweeping up everything in their orbital paths and becoming protoplanets. The final stages of planet formation can be violent, with massive collisions between protoplanets that can melt entire worlds, strip away atmospheres, or create moons. Earth's moon, for example, is thought to have formed from such a collision. By the time a planetary system is 50 to 100 million years old, most of the planet formation is complete, though smaller bodies continue to collide and evolve, and even after planets form, they continue to be shaped by impacts. Planets continue to be bombarded by asteroids and comets long after formation. Even after the main phase of planet formation ends, the solar system remains a chaotic place. Leftover planetesimals, asteroids and comets continue to orbit the Sun, and occasionally their paths cross with those of planets. These impacts can have profound effects. Large collisions can alter a planet's rotation, strip away parts of its atmosphere, or deliver water and organic molecules to its surface. Earth, for instance, went through a period called the Late Heavy Bombardment about 4 billion years ago, when the inner solar system experienced a spike in impacts. Some scientists believe this bombardment delivered much of Earth's water brought in by icy comets from the outer solar system. The Moon's surface still bears the scars of this period, with large impact basins visible even from Earth. Mars too shows evidence of ancient impacts that shaped its surface. Over time, the frequency of impacts decreases as the solar system clears out its debris, but impacts never stop entirely. Even today, asteroids occasionally strike planets, and comets dive into the Sun. And one of the most dramatic collisions in our solar system's history gave Earth its moon. Earth's moon likely formed from debris after a Mars-sized object collided with early Earth. This event, called the Giant Impact, occurred about 4.5 billion years ago, not long after Earth itself had formed. The impactor, sometimes called Theia, struck Earth at an oblique angle, and the collision was so violent that it vaporized much of both bodies. Massive amounts of debris, molten rock, and vapor were ejected into orbit around Earth. Over time, this debris cooled and coalesced, pulled together by gravity, forming the Moon. Evidence for this theory comes from several sources. The Moon's composition is similar to Earth's mantle. Its iron core is much smaller than expected for a body that formed independently, and samples brought back by Apollo astronauts show that Moon rocks have the same oxygen isotope ratios as Earth rocks, suggesting a shared origin. The giant impact also explains why the Earth-Moon system has so much angular momentum and why the Moon is unusually large compared to Earth. It's a reminder of how violent and chaotic the early solar system was, and throughout this chaos, one planet played a protective role. Jupiter's gravity has protected inner planets by deflecting many comets and asteroids. Jupiter's immense mass gives it a gravitational influence that extends far into the solar system. Comets and asteroids that wander too close to Jupiter are often captured, deflected onto different orbits, or even ejected from the solar system entirely. This has reduced the number of impacts on Earth and the other inner planets over billions of years. Some comets have been observed falling directly into Jupiter, such as Comet Shoemaker-Levy 9 in 1994, which broke apart and slammed into Jupiter's atmosphere in a spectacular series of impacts. Each impact released energy equivalent to millions of nuclear bombs, leaving dark scars in Jupiter's clouds that were visible for months. Without Jupiter's protective presence, Earth would have experienced many more impacts, possibly making it harder for life to evolve and thrive. Jupiter acts as a gravitational shield, a cosmic guardian that quietly keeps the inner solar system a bit safer. However, Jupiter's influence has also reshaped the solar system in other ways. Planetary migration means planets can move significantly from where they originally formed. In the early solar system, interactions between planets and the protoplanetary disk, as well as gravitational interactions between planets themselves, can cause them to migrate inward or outward from their original orbits. Gas giants in particular can spiral inward as they interact with the gas in the disk, losing angular momentum and drifting toward the star. This process, called Type II migration, can move a giant planet from the outer reaches of a system to a very close orbit in just a few million years. Conversely, planets can also migrate outward through gravitational interactions with other planets or by scattering smaller bodies. In our own solar system, models suggest that Jupiter migrated inward somewhat before being pulled back outward by interactions with Saturn, an event that may have triggered the late heavy bombardment. Planetary migration has profound effects on the architecture of a planetary system, determining where planets end up and which orbits are stable. And one dramatic result of migration is the creation of hot Jupiters. Some gas giants migrate inward to become hot Jupiters. These are gas giant planets that orbit extremely close to their stars, sometimes closer than Mercury orbits the Sun, with orbital periods of just a few days. Hot Jupiters are too close to their stars to have formed there, as the intense heat and stellar radiation would have prevented the accumulation of gas during planet formation. Instead, they must have formed farther out, in the cooler regions beyond the frost line, and then migrated inward. This migration can be driven by interactions with the protoplanetary disk, which creates drag and causes the planet to spiral inward, or by gravitational interactions with other planets that alter the orbit over time. Once a hot Jupiter reaches a close orbit, tidal forces between the planet and the star can circularize the orbit and lock the planet in place. These planets are scorching hot, with dayside temperatures often exceeding 2000 degrees Fahrenheit. Their atmospheres can be stripped away by the intense stellar radiation, and they may have exotic weather, including winds that carry heat from the dayside to the night side. Hot Jupiters were among the first exoplanets discovered, and their existence reshaped our understanding of how planetary systems evolve. However, migration can also lead to more violent outcomes. Planets can be ejected from their solar systems through gravitational interactions. When multiple planets form in a system, their gravitational pulls on each other can create instabilities, especially if their orbits are close or their masses are large. Over time, these interactions can result in dramatic orbital changes, and in some cases, one planet can be flung out of the system entirely, gaining enough velocity to escape the star's gravity and become a rogue planet, drifting through interstellar space. This process is more common in young, chaotic planetary systems, where orbits have not yet settled into stable configurations. Simulations suggest that ejected planets may be quite common, and some estimates indicate there could be billions of rogue planets wandering the galaxy. These planets are dark, cold, and incredibly difficult to detect since they don't orbit a star and emit very little light. Some may retain internal heat for billions of years, keeping subsurface oceans warm beneath frozen surfaces. And the history of our own solar system includes periods of significant orbital upheaval. The NICE model suggests our gas giants once orbited much closer together. Named after the French city where the theory was developed, the NICE model proposes that in the early solar system, Jupiter, Saturn, Uranus, and Neptune were in more compact orbits than they are today. According to the model, about 600 million years after the solar system formed, gravitational interactions between the planets and a disk of icy planetesimals beyond Neptune caused the planets to migrate. Jupiter moved slightly inward, while Saturn, Uranus, and Neptune moved outward. This migration disrupted the orbits of countless small bodies in the outer solar system, sending them careening through the inner solar system and causing the late heavy bombardment. The model also explains why Neptune is farther from the Sun than Uranus. Despite likely forming closer in, it was scattered outward by gravitational encounters. The NICE model has been successful in explaining many features of the solar system, including the distribution of asteroids and Kuiper belt objects, the orbits of irregular moons, and the timing of impact craters on the Moon and terrestrial planets. It's a reminder that the solar system we see today is not how it began, and planetary atmospheres too have changed dramatically over time. Mars may have lost its thick atmosphere after its magnetic field shut down. Early in Mars's history, the planet likely had a much thicker atmosphere, possibly thick enough to support liquid water on its surface. Evidence from ancient river valleys, lake beds, and minerals that form in the presence of water suggests Mars was once warmer and wetter. However, Mars is much smaller than Earth, and its interior cooled more quickly. As the planet's core solidified, it stopped generating a global magnetic field. Without this protective magnetic field, the Martian atmosphere was exposed to the solar wind, a stream of charged particles flowing from the Sun. Over millions of years, the solar wind stripped away much of Mars's atmosphere, carrying it off into space. The planet gradually became the cold, dry world we see today, with only a thin atmosphere remaining. Some of the lost atmosphere may have been incorporated into the surface as minerals or frozen into the polar ice caps, but much of it is simply gone, blown away by the relentless solar wind. This loss of atmosphere drastically changed Mars's climate and habitability. Meanwhile, Venus experienced a different atmospheric transformation. Venus may have once had oceans before its runaway greenhouse effect. Early in Venus's history, when the Sun was cooler and less luminous, Venus may have been within the habitable zone, with surface temperatures cool enough for liquid water to exist. Some models suggest Venus could have maintained stable oceans for as long as 2 billion years. However, as the Sun gradually brightened over time, Venus received more and more heat. Water on the surface began to evaporate, and water vapor, a potent greenhouse gas, accumulated in the atmosphere. This increased the greenhouse effect, trapping even more heat, causing more evaporation, in a self-reinforcing feedback loop. Eventually, the oceans evaporated entirely, and the water vapor was broken apart by ultraviolet light from the Sun, with the hydrogen escaping into space and the oxygen reacting with surface rocks. What remained was a dense carbon dioxide-rich atmosphere and a scorching hot surface. Venus's story is a cautionary tale of how a planet's climate can spiral out of control, transforming a potentially habitable world into a hellish furnace. And Venus is not the only planet to lose its atmosphere. Planetary atmospheres can be stripped away by stellar winds. Stars, especially young and active ones, emit streams of charged particles called stellar winds. These winds can interact with a planet's atmosphere, particularly if the planet lacks a strong magnetic field to deflect them. The charged particles collide with atmospheric molecules, transferring energy and gradually eroding the atmosphere over millions or billions of years. This process, called atmospheric escape, has affected many planets and moons. Mars, as we've discussed, lost much of its atmosphere this way. Even Earth loses small amounts of atmosphere to space, though our magnetic field protects us from the worst of it. On exoplanets orbiting close to their stars, especially around active red dwarf stars that produce powerful flares, atmospheric stripping can be severe and rapid. Some hot Jupiters have been observed with extended atmospheres that stream away like comet tails, losing thousands of tons of gas every second. Whether a planet can retain its atmosphere depends on its mass, its distance from the star, the strength of its magnetic field, and the activity level of its host star. And over time, tidal forces also play a role in shaping planetary systems. Tidal forces can cause moons and planets to gradually change their orbits. Tidal forces arise when the gravitational pull on one side of an object is stronger than on the other side, creating a stretching effect. For planets and moons, this stretching causes internal friction, which generates heat and dissipates energy. This energy loss affects the orbits. For example, Earth's moon creates tides in Earth's oceans, and the friction from these tides slows Earth's rotation and causes the moon to gradually move away from Earth. Over billions of years, this process has lengthened Earth's day and pushed the moon about 1.5 inches farther away each year. Similarly, tidal forces can cause moons to spiral inward if they orbit in the opposite direction of their planet's rotation, as is the case with Neptune's moon Triton. Tidal heating can also keep moons geologically active, as seen on Jupiter's moon Io, where tidal flexing generates enough heat to drive intense volcanic activity. Tidal forces are subtle but persistent, shaping the long-term evolution of planetary systems. And as we shift our focus to exoplanets, these same forces continue to play a role. The first confirmed exoplanet around a Sun-like star was discovered in 1995. Astronomers Michel Mayor and Didier Queloz detected the planet, named 51 Pegasi b using the radial velocity method, observing the subtle wobble in the star's motion caused by the gravitational pull of an orbiting planet. The discovery was groundbreaking because it proved that planets exist around other stars, something that had been theorized but never confirmed. 51 Pegasi b was also surprising. It's a gas giant similar in mass to Jupiter, but it orbits its star in just over 4 days, much closer than Mercury orbits the Sun. This was the first hot Jupiter ever discovered, and its existence challenged existing theories of planet formation. Astronomers had assumed gas giants would only form far from their stars, but 51 Pegasi b showed that planets could migrate inward to very close orbits. The discovery opened the floodgates, and within a few years, dozens of exoplanets were being discovered. Mayor and Queloz were awarded the Nobel Prize in Physics in 2019 for their discovery. And since then, the number of known exoplanets has grown exponentially. Over 5,600 exoplanets have been confirmed as of 2024. This number represents a revolution in astronomy. Just a few decades ago, we knew of no planets beyond our solar system. Now we know they are common, orbiting most stars in the galaxy. These confirmed exoplanets range from small, rocky worlds smaller than Earth to massive gas giants larger than Jupiter. They orbit at distances ranging from a few stellar radii to hundreds of astronomical units. Some orbit stable, sun-like stars, while others orbit red dwarfs, binary stars, or even the remnants of dead stars. The diversity is staggering, and every new discovery adds to our understanding of how planets form and evolve. The confirmed planets represent only a fraction of what's out there. There are thousands more candidate exoplanets awaiting confirmation, and missions like TESS and future telescopes will continue to add to the count. Each planet is a new data point, a new piece of the puzzle, helping us understand not just other solar systems, but our own place in the universe. And one mission in particular revolutionized exoplanet detection. The Kepler Space Telescope discovered over 2,700 confirmed exoplanets. Launched in 2009, Kepler was designed to stare at a single patch of sky containing about 150,000 stars, continuously monitoring their brightness to detect the tiny dips caused when planets pass in front of them. This technique, called the transit method, is incredibly sensitive and can detect planets as small as Earth. Over its mission, Kepler identified thousands of candidate planets, many of which have been confirmed through follow-up observations. Kepler's discoveries include a wide variety of worlds, super-Earths, mini-Neptunes, hot Jupiters, and even some planets in the habitable zones of their stars. The mission also revealed that small planets are more common than large ones, and that multi-planet systems are the norm rather than the exception. Kepler ran out of fuel in 2018, but its legacy continues. The data it collected is still being analysed, yielding new discoveries years after the mission ended. Kepler fundamentally changed our understanding of planetary systems, showing us that the galaxy is teeming with worlds, and the transit method remains one of our most powerful tools for finding planets. Most exoplanets are discovered using the transit method, watching for tiny dips in starlight. When a planet passes in front of its star as seen from Earth, it blocks a small fraction of the star's light, causing a brief dimming. The amount of dimming depends on the size of the planet relative to the star. A planet the size of Jupiter might block about 1% of the star's light, while an Earth-sized planet might block only 0.01%. These dips are repeating and regular, occurring every time the planet completes an orbit. By measuring the timing, depth, and duration of these transits, astronomers can determine the planet's size, orbital period, and distance from the star. The transit method works best for planets that orbit close to their stars, where transits are more frequent and easier to detect. It also requires the planet's orbit to be aligned with our line of sight, so we only detect a small fraction of the planets that actually exist. Still, the method has been extraordinarily successful, responsible for the majority of confirmed exoplanet discoveries, and it's complemented by another powerful technique. The radial velocity method detects planets by measuring a star's wobble. As a planet orbits a star, it doesn't actually orbit around the star's center. Both the planet and the star orbit around their common center of mass. For a star with a planet, this causes the star to move slightly, wobbling back and forth as the planet orbits. This wobble is tiny, often just a few meters per second, but it can be detected by observing the star's spectrum. As the star moves toward us, its light is slightly blue shifted, and as it moves away, its light is red shifted due to the Doppler effect. By measuring these shifts over time, astronomers can infer the presence of a planet, determine its orbital period, and estimate its mass. The radial velocity method was the first technique used to discover exoplanets and remains important today, especially for detecting massive planets that cause larger wobbles. It's less sensitive to small planets than the transit method, but it works for planets at any orbital distance, not just those that transit, and some planets have particularly unusual orbits. Some exoplanets orbit two stars at once, called circumbinary planets. In binary star systems, where two stars orbit each other, planets can form in two ways. They can orbit one of the stars closely, or they can orbit both stars at a greater distance. Circumbinary planets orbit both stars, tracing a path around the pair as if they were a single gravitational object. These planets experience complex gravitational dynamics, with their orbits perturbed by the changing positions of both stars. The environment is chaotic, and stable orbits are only possible at certain distances. Kepler discovered several circumbinary planets, including Kepler 16b, which orbits two stars similar to the fictional planet Tatooine from Star Wars. From the surface of such a planet, you would see two suns in the sky, rising and setting at different times, casting multiple shadows. The discovery of circumbinary planets showed that planet formation is possible even in complex multi-star systems, which make up a significant fraction of the stars in the galaxy. And among the diversity of exoplanets, certain types have become particularly intriguing. Super-Earths are rocky planets larger than Earth but smaller than Neptune. They typically have masses between 1 and 10 times that of Earth and are made primarily of rock and metal, though some may have thick atmospheres or even layers of water ice. Super-Earths are one of the most common types of exoplanets, yet they don't exist in our solar system, making them especially interesting. Their size suggests they could have stronger gravity, thicker atmospheres, and more active geology than Earth. Some super-Earths orbit within the habitable zones of their stars, making them candidates for liquid water and potentially life. However, not all super-Earths are habitable. Many orbit too close to their stars and are scorching hot, or they have thick hydrogen atmospheres that would make them more like mini gas giants. The term super-Earth refers only to size and mass. not to habitability or surface conditions. Still, these planets represent a bridge between small rocky worlds like Earth and the larger ice giants like Uranus and Neptune. And another common category blurs the line even further. Mini-Neptunes are small gas planets between Earth and Neptune in size. They are larger than super-Earths but smaller than Neptune, typically with masses between 10 and 20 times that of Earth. These planets likely have rocky or icy cores surrounded by thick atmospheres of hydrogen, helium, and other gases. Mini-Neptunes are extremely common, possibly the most abundant type of planet in the galaxy. However, we don't have one in our solar system, so they remain somewhat mysterious. Their atmospheres may vary widely. Some could be dominated by hydrogen and helium, others by water vapor or more exotic compounds. Some mini-Neptunes may have surface conditions that are hostile to life, with crushing atmospheric pressures and no solid surface to stand on. Others might have lost their thick atmospheres over time, leaving behind a rocky core, a process called photoevaporation. Understanding mini-Neptunes is key to understanding planetary formation because they seem to represent a transition phase between rocky planets and gas giants, and at the extreme end of planetary diversity are the hot Jupiters. Hot Jupiters orbit extremely close to their stars with years lasting only days. These gas giants are similar in size and composition to Jupiter, but they orbit their stars at distances closer than Mercury orbits the Sun. As a result, their orbital periods are incredibly short, often just a few days or even hours. Hot Jupiters are tidally locked, with one side permanently facing the star and the other in perpetual darkness. The day side can reach temperatures exceeding 2000 degrees Fahrenheit, hot enough to vaporize metals like iron and silicates like sand. The night side is much cooler, creating extreme temperature gradients that drive powerful winds. These winds can reach thousands of miles per hour, redistributing heat around the planet and creating dynamic, turbulent atmospheres. Hot Jupiters are thought to have formed farther from their stars and migrated inward, a process that makes their orbits circular and stable. They were among the first exoplanets discovered because their size and close orbits make them easy to detect, and their extreme conditions have taught us much about atmospheric physics. Some exoplanets are tidally locked with permanent day and night sides. Tidal locking occurs when a planet's rotation period matches its orbital period, so the same side always faces the star. This is common for planets that orbit close to their stars, where tidal forces are strong. On a tidally locked planet, one hemisphere experiences endless daylight, baking under the constant glare of the sun, while the other hemisphere is plunged into eternal night, freezing in the absence of sunlight. Between these extremes lies a twilight zone, a ring around the planet where the sun hangs perpetually on the horizon. This region might have the most temperate conditions, with temperatures that could allow for liquid water, even if the rest of the planet is inhospitable. Tidal locking has implications for habitability. The day side might be too hot, the night side too cold, but the twilight zone could be a haven for life. Some scientists believe that tidally locked planets around red dwarf stars could be prime candidates for habitability, despite their unusual conditions. And among the most exciting discoveries are systems with multiple small planets. TRAPPIST-1 system contains 7 Earth-sized planets orbiting an ultra-cool dwarf star. Discovered in 2017, this system is located about 40 light-years away and represents one of the most exciting finds in exoplanet science. All 7 planets are roughly the size of Earth, and they orbit a star that's only slightly larger than Jupiter, though much more massive. The star is cool and dim, a red dwarf that glows faintly in infrared light. Because the star is so small and cool, the planets orbit very close to it, with all 7 packed into a space smaller than the orbit of Mercury. Despite their proximity to the star, several of the planets receive similar amounts of energy to what Earth receives from the Sun. The system is remarkably compact, and the planets are in orbital resonance with each other, creating a gravitational harmony that keeps their orbits stable. From the surface of one planet, you might see other planets in the sky, appearing larger than our Moon. TRAPPIST-1 has become a prime target for studying potentially habitable worlds. And what makes this system even more intriguing is that several of these planets lie in the habitable zone. 3 planets in the TRAPPIST-1 system lie within the habitable zone. These planets, designated TRAPPIST-1e, 1f and 1g, orbit at distances where temperatures could allow liquid water to exist on their surfaces, assuming they have atmospheres and the right conditions. TRAPPIST-1e, in particular, receives a similar amount of stellar energy as Earth does from the Sun, making it one of the most promising candidates for habitability. All 3 planets are likely rocky, based on their masses and sizes, and they may have atmospheres, though we don't yet know their compositions. The James Webb Space Telescope has begun studying these planets, searching for signs of atmospheres and looking for biosignature gases that might indicate life. If these planets have water, thick atmospheres, and stable climates, they could potentially harbour life, though the red dwarf star's frequent flares pose challenges. The discovery of TRAPPIST-1 showed that small cool stars can host multiple terrestrial planets in close orbits, expanding the number of potentially habitable worlds in the galaxy. And while TRAPPIST-1 is exciting, another exoplanet holds the distinction of being our closest neighbour. Proxima Centauri b is the closest known exoplanet to Earth at 4.24 light-years away. It orbits Proxima Centauri, a red dwarf star that is part of the Alpha Centauri system, our Sun's nearest stellar neighbour. Discovered in 2016, Proxima Centauri b has a minimum mass about 1.3 times that of Earth, suggesting it's a rocky planet. It orbits its star every 11.2 days, which places it within the habitable zone despite the close orbit because Proxima Centauri is much cooler and dimmer than the Sun. However, Proxima Centauri is an active star, producing powerful flares that could strip away the planet's atmosphere or sterilize its surface with radiation. Whether Proxima Centauri b has an atmosphere and whether it could support life remains unknown. The planet has become a target for future studies, and some scientists have even proposed sending tiny spacecraft to the Alpha Centauri system to take close-up images within our lifetimes. Being so close, Proxima Centauri b represents humanity's best chance for directly observing an exoplanet in detail. And while some planets orbit solitary stars, others exist in crowded stellar neighborhoods. Some exoplanets orbit stars in dense clusters containing thousands of suns. Star clusters are regions where hundreds or thousands of stars are packed closely together, formed from the same giant cloud of gas. For a long time, astronomers weren't sure if planets could form or survive in such chaotic environments, where close encounters with other stars could disrupt planetary systems. However, exoplanets have been found even in these crowded conditions, proving that planets are resilient. In dense clusters, the night sky would be spectacular, filled with bright stars visible even during the day. A planet in such an environment might experience gravitational perturbations from passing stars, potentially altering its orbit over time. Radiation from nearby massive stars could also affect the planet's atmosphere. Despite these challenges, planets persist, orbiting their stars in the bustling heart of stellar nurseries and ancient globular clusters. These discoveries suggest that planets can form and survive in a wide range of environments, even the most extreme. And some planets don't orbit any star at all. Rogue planets drift through space without orbiting any star. These solitary worlds have been ejected from their home systems, cast out by gravitational interactions with other planets or by close encounters with passing stars. Once freed from their star's gravity, they wander through the galaxy, dark and cold, invisible except for the faint heat they retain from their formation. Rogue planets are difficult to detect because they don't reflect starlight and emit very little infrared radiation. However, astronomers have found evidence of several rogue planets using gravitational microlensing, a technique that detects the brief brightening of a background star when a massive object passes in front of it. Some rogue planets may have been ejected shortly after formation, while others might have drifted for billions of years. Despite being isolated from any sun, some rogue planets could retain enough internal heat to maintain subsurface oceans beneath thick ice shells, potentially even supporting microbial life in the dark. These wanderers remind us that not all planets follow the rules. Some journey alone, and there may be far more of them than we ever imagined. There may be billions of rogue planets in our galaxy alone. Estimates based on gravitational microlensing surveys and simulations of planetary system formation suggest that ejected planets could be more common than stars. For every star in the Milky Way, there might be one or more rogue planets drifting through interstellar space. These planets span a range of sizes, from small rocky worlds to massive gas giants. Most are completely dark, detectable only by their gravitational influence. Some may have been ejected as fully formed planets, while others might be planetary embryos that never grew large enough to clear their orbits. The sheer number of rogue planets implies that planet formation is a violent and chaotic process, with many worlds cast out during the tumultuous early stages of system evolution. It also means the galaxy is far more populated than we once thought, filled not just with stars and planets, but with countless wandering worlds, silent and unseen, drifting through the void. And while most planets remain hidden, we've begun to glimpse a few directly. Some exoplanets have been directly imaged using advanced telescope techniques. Most exoplanets are detected indirectly through their effects on starlight, but a small number have been photographed directly. This is incredibly difficult because planets are millions or billions of times fainter than their host stars, and they're usually very close to the star in the sky. To image an exoplanet directly, astronomers use coronagraphs or star shades to block the star's light, along with adaptive optics to correct for atmospheric distortion. The planets that have been imaged are typically young, massive gas giants that still glow with heat from their formation, making them bright enough in infrared light to be detected. One famous example is the HR 8799 system, where 4 giant planets have been directly imaged orbiting a young star. Watching these planets move over the years has confirmed their orbits and provided insights into their atmospheres and compositions. Direct imaging is the future of exoplanet science, as it will allow us to study planets in detail, analyze their atmospheres, and search for signs of life. And even without direct images, we can still study exoplanet atmospheres. Exoplanet atmospheres can be analysed by studying light filtering through them during transits. When a planet passes in front of its star, some of the starlight passes through the planet's atmosphere before reaching us. Different molecules in the atmosphere absorb specific wavelengths of light, leaving fingerprints in the spectrum. By comparing the spectrum of the star with and without the planet in front of it, astronomers can identify which gases are present. This technique, called transmission spectroscopy, has revealed the presence of water vapor, carbon dioxide, methane, sodium, and other compounds in the atmospheres of several exoplanets. The technique works best for large planets with thick atmospheres like hot Jupiters, but it's becoming sensitive enough to study smaller planets as well. Each molecule absorbs light in a unique way, creating a chemical signature that can be detected even from hundreds of light years away. It's a remarkable feat of observation, allowing us to study the air of distant worlds without ever visiting them. And one of the most exciting discoveries has been the detection of water. Scientists have detected water vapor in several exoplanet atmospheres. Water is essential for life as we know it, so finding it on other worlds is a key step in the search for habitable planets. Water vapor has been detected on hot Jupiters, where it exists as a gas in the scorching atmospheres, and on some smaller planets that might be more temperate. One notable example is K218b, a super-Earth or mini-Neptune where water vapor was detected in the atmosphere, along with the possibility of liquid water clouds. The planet orbits in the habitable zone of its star, raising the intriguing possibility that it could have conditions suitable for life, though much remains uncertain about its surface and atmospheric structure. Detecting water vapor on smaller, cooler planets is challenging, but as our instruments improve, we'll be able to study more Earth-like worlds and determine whether they have the right conditions for liquid water on their surfaces. Water is common in the universe, found in comets, moons, and interstellar clouds, so its presence on exoplanets is not surprising. What matters is whether that water exists in a form that could support life. And as we develop better tools, our ability to study these distant atmospheres continues to improve. The James Webb Space Telescope is revolutionizing exoplanet atmospheric studies. Launched in 2021, Webb is the most powerful space telescope ever built, with a large mirror and sensitive infrared instruments that can detect the faint light from exoplanets and analyze their atmospheres in unprecedented detail. Webb has already observed several exoplanets, including hot Jupiters and some smaller worlds, detecting molecules like water, carbon dioxide, and sulfur dioxide. One of Webb's key goals is to study the atmospheres of rocky planets in the habitable zones of their stars, searching for biosignatures, gases that might indicate the presence of life, such as oxygen, methane, or phosphine in unusual abundances. Webb can also study the climates of exoplanets, mapping temperature variations across their surfaces and looking for clouds, winds, and weather patterns. The data Webb provides will help astronomers determine which exoplanets are most likely to be habitable and where we should focus future searches for life. It's a transformative tool, opening a new era in the study of distant worlds. And some of those worlds have conditions more extreme than we ever imagined. HD 189733b experiences winds up to 5,400 miles per hour and may rain molten glass sideways. This hot Jupiter orbits its star every 2.2 days, and its atmosphere is a nightmare of extreme weather. The planet is tidally locked, with one side always facing the star and the other in darkness. The temperature difference between the day and night sides drives incredibly powerful winds that whip around the planet at supersonic speeds, carrying heat from the scorching day side to the cooler night side. Suspended in the atmosphere are tiny particles of silicate, the mineral that forms glass. On the day side, these particles are vaporized, but as the winds carry them to the cooler night side, they condense into tiny droplets or crystals of molten glass, which then fall as rain. However, the winds are so strong that the glass rain doesn't fall straight down. It's blown sideways at thousands of miles per hour, creating horizontal sheets of glassy shards. From a distance, HD 189733b looks deceptively beautiful, a soft blue color similar to Earth, caused by the scattering of light by the silicate particles. But up close, it's one of the most hostile places imaginable. And yet, even more extreme planets exist. Kelt 9b is hotter than most stars, with temperatures exceeding 7,800 degrees Fahrenheit. This ultra-hot Jupiter orbits extremely close to its massive blue host star, completing an orbit in just 1.5 days. The planet is so hot that molecules in its atmosphere, like hydrogen and water, break apart into their constituent atoms. Even heavier molecules like iron and titanium can exist as gases, and some of these metals may condense into clouds at certain altitudes. The day side of KELT 9b is hotter than the surfaces of many red dwarf stars, making it one of the most extreme environments known. The planet is also slowly evaporating, losing mass as its atmosphere is blasted away by the intense radiation from its star. Over time, KELT 9b may be stripped down to a rocky core, or it may be completely destroyed. Studying planets like KELT 9b helps scientists understand the limits of planetary atmospheres and how planets behave under the most extreme conditions. It blurs the line between planets and stars, a world on the edge of existence. And some planets may have interiors as exotic as their atmospheres. 55 Cancri E might have a surface covered partially in graphite and diamond. This super-Earth orbits its star every 18 hours, making it one of the fastest orbiting planets known. It's about twice the size of Earth and roughly 8 times as massive. What makes 55 Cancri E especially intriguing is its composition. The planet is thought to be rich in carbon, and models suggest that under the extreme pressures and temperatures in its interior, carbon could exist in the form of diamond and graphite. The surface might be covered in a layer of graphite, while deeper inside, there could be vast regions of crystalline diamond. The planet's day side, which always faces the star, reaches temperatures around 4,400 degrees Fahrenheit, hot enough to melt the surface into a magma-like state. The night side is cooler but still scorching. 55 Cancri E also shows evidence of volcanic activity, possibly releasing vaporized silicates into the atmosphere. It's a world where geology becomes almost unrecognizable, where the very ground might glitter with carbon crystals. And yet, in terms of strangeness, some planets defy even these extremes. WASP 76b is hot enough that iron vaporizes on the day side and rains down on the night side. This hot Jupiter is tidally locked, with the day side exposed to scorching temperatures exceeding 4,000 degrees Fahrenheit. At these temperatures, metals like iron can vaporize and exist as gases in the atmosphere. Powerful winds, driven by the temperature difference between day and night, carry this vaporized iron from the day side to the night side. As the iron moves into the cooler night side, where temperatures drop to around 2,700 degrees Fahrenheit, it condenses into liquid droplets and falls as rain. Imagine standing on the night side of WASP 76b, looking up into the twilight zone between day and night, and seeing a rain of molten iron falling from the sky. Spectroscopic observations have confirmed the presence of iron vapor on the day side and its absence on the night side, consistent with the iron rain hypothesis. WASP 76b is a world of elemental fury, where the very atmosphere is made of materials that are solid and familiar on Earth, but here exist in states we can barely imagine. And some planets orbit in even stranger environments. PSRB 1257 plus 12 planets orbit a pulsar, the collapsed core of an exploded star. Pulsars are neutron stars, incredibly dense remnants left behind after a massive star goes supernova. They spin rapidly, sometimes hundreds of times per second, and emit beams of radiation from their magnetic poles. If these beams sweep across Earth, we detect them as regular pulses, like a cosmic lighthouse. In 1992, astronomers discovered planets orbiting PSR b 1257+12, the first confirmed exoplanets ever detected. These planets are thought to be second-generation worlds, formed from the debris left over after the supernova, or possibly the remnants of a companion star that was destroyed. The environment around a pulsar is harsh, bathed in intense radiation and magnetic fields, making these planets utterly inhospitable. They orbit in eerie silence, circling a dead star that pulses with the energy of its violent past. The discovery of pulsar planets was unexpected and opened the door to the idea that planets could form in the aftermath of stellar death. And some planets exist in conditions almost as extreme. TRS-2b is darker than coal, reflecting less than 1% of light that hits it. This hot Jupiter is one of the darkest planets ever discovered, absorbing nearly all the starlight that reaches it. The reason for its extreme darkness is still not fully understood, but it's thought to be due to the presence of light-absorbing chemicals in its atmosphere, such as vaporized sodium, potassium, or titanium oxide. These chemicals may form clouds or hazes that trap light rather than reflecting it. TRS-2b orbits very close to its star, with surface temperatures around 1,800 degrees Fahrenheit, hot enough to glow faintly with its own thermal radiation. In visible light, the planet would appear as a nearly black sphere, a dark shadow against the backdrop of space. If you could see it up close, you might detect a faint reddish glow from the heat, but otherwise, it would be almost invisible. TRS-2b challenges our assumptions about planetary atmospheres and shows that planets can come in appearances we never expected. And while some planets are dark, others may be covered entirely in water. GJ1214b might be a water world with a planet-wide ocean hundreds of miles deep. This super-Earth orbits a red dwarf star about 48 light-years away, and it's roughly 2.7 times the size of Earth, with a mass about 6.5 times greater. Its density is too low to be purely rocky, suggesting it has a significant amount of water or other volatiles. Models indicate that GJ1214b could be covered by a global ocean tens or even hundreds of miles deep, with no land in sight. Beneath the ocean, the immense pressure would compress the water into exotic forms of ice, even though the temperatures are far too high for normal ice. The planet's atmosphere is thick and hazy, likely filled with water vapor and clouds, making it difficult to study the surface. If GJ1214b is indeed a water world, it represents a class of planets that may be common in the galaxy, but doesn't exist in our solar system. These worlds could have subsurface oceans warmed by internal heat, possibly even hosting life in the dark, pressurized depths. And some planets may have skies filled with gemstone clouds. HAT-P7b may have clouds made of corundum, the mineral that forms rubies and sapphires. This hot Jupiter orbits its star every 2.2 days, and temperatures in its atmosphere reach around 4,600 degrees Fahrenheit. At these extreme temperatures, minerals that would normally be solid, like aluminum oxide, corundum, can exist as vapor. As the vapor rises and cools in the upper atmosphere, it condenses into tiny crystals, forming clouds. On Earth, corundum with trace amounts of chromium forms rubies, and with iron and titanium, it forms sapphires. On HAT-P7b, these gemstone clouds may shimmer in the upper atmosphere, though they wouldn't sparkle the way we imagine. The environment is far too hot and chaotic for that. Observations have shown that HATP7b has varying cloud cover, with winds pushing clouds from the day side to the night side, creating changing weather patterns. The idea of gemstone clouds is almost poetic, a reminder that the universe creates beauty in the most unexpected places. And some planets have skies we recognize from science fiction. Kepler-16b orbits two suns like Tatooine from Star Wars. This circumbinary planet orbits a pair of stars that are themselves orbiting each other, creating a system where the planet experiences double sunrises and double sunsets. Kepler-16b is a gas giant, roughly the size of Saturn, and it orbits its two stars every 229 days. The two stars are smaller and cooler than the Sun. One is about 69% the mass of the Sun, and the other is about 20%. They orbit each other every 41 days, and Kepler-16b circles them both at a distance where the gravitational influences of both stars are balanced. From the surface of a moon orbiting Kepler-16b, if such a moon existed, you would see two suns moving across the sky, casting double shadows and creating a light cycle unlike anything we experience on Earth. The discovery of Kepler-16b and other circumbinary planets showed that the iconic double sunset from Star Wars is not just fiction, it's a real possibility, and while some planets have long stable futures, others are doomed. WASP-12b is being slowly consumed by its star and will be destroyed within 10 million years. This hot Jupiter orbits so close to its star that tidal forces are stretching it into an egg shape, and the intense stellar radiation is heating its atmosphere to over 4,000 degrees Fahrenheit. The planet is losing mass at an alarming rate, with material from its atmosphere being pulled away by the star's gravity and falling onto the star's surface. Observations show that WASP-12b is surrounded by a cloud of gas, and the star shows signs of absorbing this material. The planet is essentially being devoured, slowly spiraling inward as it loses mass and orbital energy. In cosmic terms, 10 million years is a short time, and WASP-12b is in its final chapter. It's a dramatic reminder that planets are not eternal. They can be destroyed by the very stars they orbit, and some planets follow orbits that are wildly eccentric. HD 80606b has the most eccentric orbit of any known planet, swinging dramatically close then far from its star. Most planets have nearly circular orbits, but HD 80606b follows a highly elongated elliptical path. At its closest approach, it comes within about 4 million miles of its star, closer than Mercury is to the Sun. At its farthest, it swings out to a distance of over 80 million miles. This extreme variation causes wild swings in temperature. When the planet is near the star, its day side heats up by over 1,000 degrees Fahrenheit in just a few hours, triggering massive shockwaves and violent storms in the atmosphere. When it's far from the star, the planet cools down again. The orbit takes 111 days to complete, and each pass near the star is a dramatic event. HD 80606b's eccentric orbit is thought to be the result of gravitational interactions with a companion star in the system, which perturb the planet's orbit over time. It's a world caught in a gravitational tug-of-war, swinging between extremes with every orbit, and some planets may have surfaces covered in molten rock. Cohorty 7b may have a surface of molten lava with a rocky vapor atmosphere. This super-Earth orbits extremely close to its star, completing an orbit in just 20 hours. It's tidally locked, with the day side perpetually facing the star and reaching temperatures around 4,000 degrees Fahrenheit. At these temperatures, rock itself can melt and vaporize. The day side of Cohorty 7b is likely covered in a molten lava ocean, glowing red and orange with heat. The intense heat vaporizes rock, creating an atmosphere made not of gas, but of vaporized silicates, sodium and potassium. This rocky vapor atmosphere is unlike anything we see on Earth, but it's a natural consequence of the planet's extreme conditions. As the vaporized rock circulates to the cooler night side, it condenses and falls as rain, raining pebbles or dust that solidify before hitting the ground. Corot 7b represents the extreme end of terrestrial planets, a world where the ground is liquid and the air is made of rock. It's a glimpse of what happens when you place a rocky planet far too close to its star, and some planets orbit even faster. Kepler 70b orbits so close to its star that its year lasts just 5.76 hours. This tiny, scorched world is one of the shortest period planets ever discovered. It orbits a hot subdwarf star, the exposed core of a red giant that has shed its outer layers. Kepler 70b is likely the remnant of a much larger planet, possibly a gas giant that survived being engulfed by the star during its red giant phase and has since been stripped down to its core. The planet's surface temperature is estimated to be around 12,000 degrees Fahrenheit, hotter than the surface of many stars. At these temperatures, the planet glows brightly and its surface may be molten or even partially vaporized. The orbit is so tight that the planet is just over 700,000 miles from the star's surface, a distance only slightly greater than the diameter of the Sun. Kepler 70b is a world on the very edge of destruction, a survivor of stellar evolution clinging to existence in the most extreme environment imaginable. And some planets are unusually large for their mass. WASP-17b is one of the largest planets known, almost twice the size of Jupiter, but with half its mass. This makes it one of the puffiest planets ever discovered, with a density lower than styrofoam. The planet orbits its star in a retrograde direction, opposite to the star's rotation, which is unusual and suggests a violent history, possibly involving gravitational interactions with other planets. WASP-17b's extreme size is likely due to intense heating from its star, which causes its atmosphere to expand dramatically. The planet's atmosphere may also contain compounds that absorb heat efficiently, preventing it from radiating away and keeping the atmosphere bloated. Despite its enormous size, WASP-17b's low mass means its surface gravity is weak and its atmosphere is slowly escaping into space. It's a planet in transition, puffed up by heat and gradually losing its outer layers. WASP-17b challenges our understanding of planetary structure and shows that planets can exist in states we once thought impossible, and some planets exist in even stranger states of matter. Gliese 436b is a hot ice planet where water exists in a hot but solid state due to extreme pressure. This Neptune-sized planet orbits a red dwarf star about 30 light-years away. Its surface temperature is around 800 degrees Fahrenheit, far too hot for water to exist as a liquid or solid under normal circumstances. However, the planet's interior is under such immense pressure that water is compressed into a form called Ice 7 or Ice 10. Exotic high-pressure ices that remain solid even at high temperatures. These ices are not like the ice we know. They're dense, hot, and crystalline, with structures that form only under extreme pressure. On Gliese 436b, the core may be rocky, surrounded by a thick layer of hot ice and topped by a hydrogen-helium atmosphere. The planet represents a bizarre state of matter that doesn't exist anywhere on Earth. It's a reminder that the universe contains materials and conditions far beyond our everyday experience. And while Gliese 436b's interior is strange, the moons of our solar system also hold mysteries. Jupiter's moon, Io, is the most volcanically active body in the solar system. Io's surface is constantly being reshaped by volcanic eruptions, with over 400 active volcanoes identified. The volcanism is driven by tidal heating. As Io orbits Jupiter, it's pulled and squeezed by the gravity of Jupiter and the other Galilean moons, causing friction and heat in its interior. This heat melts rock, creating magma that erupts onto the surface in spectacular plumes that can reach hundreds of miles into space. Io's surface is covered in sulfur and sulfur dioxide frost, giving it a yellowish, mottled appearance. Some eruptions produce lava flows hotter than any on Earth, and the moon is constantly being covered by new volcanic material, burying impact craters and keeping the surface geologically young. Io has no water, its interior is too hot, and any water that once existed has long since been driven off. The moon is a world of fire and brimstone, a volcanic hellscape orbiting the largest planet in the solar system. And while Io is dominated by fire, another moon is dominated by ice and water. Saturn's moon Enceladus shoots geysers of water ice into space from a subsurface ocean. These geysers, discovered by the Cassini spacecraft, erupt from fractures near Enceladus's south pole, called tiger stripes. The geysers spray water vapor, ice particles, and organic molecules into space, some of which escapes Enceladus entirely and contributes to Saturn's E-ring. The source of the geysers is a global ocean beneath Enceladus's icy crust, kept liquid by tidal heating from Saturn. The ocean is in contact with a rocky seafloor, creating the potential for hydrothermal activity, similar to the deep-sea vents on Earth that support unique ecosystems. The presence of organic molecules in the geyser plumes suggests that Enceladus has the ingredients necessary for life: liquid water, organic chemistry, and an energy source. Enceladus is one of the most promising places in the solar system to search for extraterrestrial life, despite its small size and frozen surface. And Enceladus is not the only large moon in the Jovian system. Jupiter's moon. Ganymede is the largest moon in the solar system, larger than Mercury. Ganymede has a diameter of 3,270 miles, making it bigger than the planet Mercury, though it's less massive because it contains a large amount of water ice. Ganymede is unique among moons because it has its own magnetic field, generated by a liquid iron core. This magnetic field creates a magnetosphere around the moon, providing some protection from Jupiter's intense radiation. Ganymede's surface is a mix of two types of terrain: dark, heavily cratered regions that are billions of years old, and brighter, grooved regions that are younger and appear to have been reshaped by tectonic activity. Beneath the surface, Ganymede is thought to have a subsurface ocean sandwiched between layers of ice. The ocean may be in contact with a rocky mantle below, raising the possibility of chemical interactions that could support life. Ganymede is a world of complexity, with an interior structure more like a planet than a moon. And Saturn too has an impressive collection of moons. Saturn has 146 confirmed moons, more than any other planet. These moons range in size from Titan, which is larger than Mercury, down to tiny moonlets just a few hundred meters across. Many of Saturn's smaller moons are embedded in the rings or orbit just beyond them, acting as shepherd moons that help maintain the ring structure. Some of Saturn's moons are captured objects, asteroids or comets that were pulled into orbit by Saturn's gravity. Others, like Titan and Enceladus, are large and geologically active. Saturn's moon system is diverse and complex, with each moon having its own unique characteristics. Some are icy and smooth, Others are heavily cratered, and a few show signs of recent geological activity. The large number of moons suggests that Saturn's formation and evolution involved capturing and accumulating material from the surrounding protoplanetary disk. And while Saturn has many moons, one of our own moon's features continues to shape Earth. Earth's moon is slowly drifting away at about 1.5 inches per year. This happens because of tidal interactions between Earth and the moon. The moon creates tides in Earth's oceans, and the friction from these tides gradually slows Earth's rotation. This lost rotational energy is transferred to the moon, increasing its orbital energy and causing it to move farther away. Billions of years ago, the moon was much closer to Earth, and Earth's day was much shorter, possibly only a few hours long. As the moon recedes, Earth's rotation continues to slow, and days gradually get longer. Eventually, in the distant future, Earth and the moon will become tidally locked to each other, with the same sides always facing each other, and the moon will stop receding. This process has been confirmed by measurements taken during the Apollo missions, when astronauts left reflectors on the moon that allow scientists to measure the Earth-Moon distance with extreme precision using laser ranging, and tidal forces have other consequences elsewhere in the solar system. Neptune's moon. Triton is the only large moon that orbits in the opposite direction of its planet's rotation. This retrograde orbit is strong evidence that Triton didn't form alongside Neptune but was captured from elsewhere, likely from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. When Triton was captured, its orbit was probably highly elliptical and chaotic. Over time, tidal forces between Neptune and Triton circularized the orbit, but the retrograde motion remained. The tidal forces that shaped Triton's orbit also generated heat in the moon's interior, possibly triggering the geological activity we see today, including the nitrogen geysers observed by Voyager 2. Triton's retrograde orbit is gradually decaying, and the moon is slowly spiraling inward toward Neptune. In about 3.6 billion years, it will cross Neptune's Roche limit and be torn apart by tidal forces, forming a spectacular ring system. Triton's story is one of capture, transformation, and eventual destruction, and other moons in our solar system face similar fates. Mars's moon Phobos will eventually crash into Mars or break apart into a ring. Phobos orbits Mars at a distance of only 3,700 miles, closer than any other moon orbits its planet. This close orbit means that tidal forces are gradually sapping Phobos's orbital energy, causing it to spiral inward by about 6 feet every century. In about 50 million years, Phobos will either collide with Mars, creating a massive impact crater, or it will cross Mars's Roche limit and be torn apart by tidal forces, forming a ring system around the planet. Phobos is heavily cratered and shows signs of fractures and grooves, possibly caused by the tidal stress it experiences. Its composition is similar to carbonaceous chondrite asteroids, suggesting it may be a captured asteroid. Phobos's fate is sealed, and Mars will one day either be impacted by its moon or adorned with rings. And all the gas giants in our solar system already have rings. All 4 gas giants in our solar system have ring systems. While Saturn's rings are the most famous and spectacular, Jupiter, Uranus, and Neptune also have rings, though they are much fainter and less extensive. Jupiter's rings are thin and made mostly of dust, likely produced by micrometeorite impacts on its inner moons. Uranus has 13 narrow, dark rings made of dust and larger particles, discovered when the planet passed in front of a star in 1977. Neptune has 5 rings, some of which contain clumps or arcs of denser material. These ring systems are dynamic, constantly being replenished by material from moons, or depleted by atmospheric drag and radiation. Rings are thought to be relatively short-lived on cosmic timescales, lasting only tens of millions of years before dissipating or falling into the planet. The presence of rings around all the gas giants suggests that rings are a natural consequence of having many moons and active environments where collisions and tidal forces can generate debris. And Saturn's rings in particular may be surprisingly young. Saturn's rings may be relatively young, perhaps only 100 million years old. This estimate comes from studies of the ring's composition and mass. The rings are extremely bright and icy, suggesting they haven't been darkened by billions of years of micrometeorite impacts and space weathering. Measurements from the Cassini spacecraft indicate that the rings are losing mass as material spirals into Saturn, a process that would have depleted them long ago if they were as old as the planet itself. The rings may have formed from the breakup of a moon or large comet that wandered too close to Saturn and was torn apart by tidal forces. Alternatively, they could be the remnants of a collision between two moons. If the rings are indeed young, they may disappear entirely in another 100 million years, making us lucky to be alive at a time when Saturn has such spectacular rings. And while Saturn's rings are unique in our solar system, some exoplanets likely have even larger ring systems. Some exoplanets likely have ring systems far larger than Saturn's. Although we haven't directly observed rings around exoplanets yet, there's good reason to believe they exist. Some exoplanet observations show unusual dips in brightness that could be caused by rings blocking starlight as the planet transits. One candidate, J1407b, may have a ring system 200 times larger than Saturn's, spanning a diameter of over 75 million miles. If confirmed, this would make it one of the most dramatic structures in the known universe. Rings around exoplanets could form from the same processes that create rings in our solar system: tidal disruption of moons, collisions, or captured material. Large ring systems could affect a planet's climate and seasons, casting shadows on the surface and altering the amount of starlight the planet receives. As our observational techniques improve, we may soon confirm the existence of these giant ring systems, adding yet another layer of diversity to the exoplanet population. And as we consider where life might exist, the concept of the habitable zone becomes important. The habitable zone is the region around a star where liquid water could exist on a planet's surface. This zone is sometimes called the Goldilocks zone because the conditions are just right, not too hot for water to boil away, and not too cold for it to freeze solid. The location and width of the habitable zone depend on the star's temperature and luminosity. Around a hot, bright star, the habitable zone is farther out. Around a cool, dim star, it's closer in. For our Sun, the habitable zone extends roughly from the orbit of Venus to the orbit of Mars, with Earth sitting comfortably in the middle. However, being in the habitable zone doesn't guarantee habitability. A planet also needs the right atmosphere, magnetic field, and geological activity to maintain conditions suitable for liquid water. Venus is technically in the habitable zone, but its runaway greenhouse effect has made it uninhabitable. Mars is on the outer edge, and it once had liquid water, but it lost its atmosphere. The habitable zone is a starting point, a guide for where to look. And red dwarf stars, which are the most common type of star, have habitable zones with unique properties. Red dwarf stars have habitable zones much closer to the star than our Sun does. Red dwarfs are small, cool stars with surface temperatures around 4,000 degrees Fahrenheit or less. Because they emit less light and heat, their habitable zones are much closer, often within a few million miles of the star. This means planets in the habitable zone of a red dwarf complete their orbits in just a few weeks or months. The proximity to the star has consequences. Planets are more likely to be tidally locked, with one side always facing the star. They're also exposed to intense stellar flares, especially around young red dwarfs, which can strip away atmospheres or bathe the surface in harmful radiation. However, red dwarfs live for trillions of years, far longer than sun-like stars, giving life ample time to evolve if it can survive the harsh conditions. Many of the most promising exoplanet candidates for habitability, like Proxima Centauri b and the TRAPPIST-1 planets, orbit red dwarfs. And tidal locking, which might seem like a barrier to habitability, may not be as limiting as once thought. Tidal locking in habitable zones might not prevent life. The twilight zone could be temperate. On a tidally locked planet, the day side is scorching hot and the night side is freezing cold, but in between lies a twilight zone where the star hangs low on the horizon, providing moderate temperatures. This ring-shaped region could have stable liquid water and relatively comfortable conditions. Winds driven by the temperature difference between day and night might redistribute heat, preventing the night side from freezing solid and the day side from becoming too hot. Some models suggest that planets with thick atmospheres could have more evenly distributed temperatures, even if they're tidally locked. Life, if it exists on such worlds, might be concentrated in the twilight zone, or it might adapt to the extreme conditions on the day or night sides. Tidal locking is common for planets orbiting red dwarfs, so if life can thrive on tidally locked worlds, it vastly increases the number of potentially habitable planets in the galaxy. And beyond surface oceans, subsurface oceans may be even more common. Subsurface oceans may be more common than surface oceans in the galaxy. Many moons in our solar system, including Europa, Enceladus, Ganymede, and possibly others, have liquid water oceans hidden beneath thick ice shells. These oceans are kept warm by tidal heating, the gravitational interactions between the moon and its planet generating internal friction and heat. Subsurface oceans could exist on exoplanets and exomoons throughout the galaxy, even on worlds far from their stars where surface temperatures are well below freezing. These hidden oceans are shielded from harmful radiation and extreme temperature swings, providing stable environments that could support life. Detecting subsurface oceans on exoplanets is challenging, but future missions may be able to identify their presence through gravitational measurements, magnetic field observations, or surface features like geysers or cryovolcanoes. If subsurface oceans are common, the number of potentially habitable worlds in the galaxy could be much higher than we currently estimate. And several moons in our own solar system are prime candidates for hosting life. Europa, Enceladus, and Titan are considered potential homes for microbial life. Europa's subsurface ocean is in contact with a rocky seafloor, creating the possibility of hydrothermal vents similar to those on Earth that support unique ecosystems. Enceladus has geysers that spray water and organic molecules into space, suggesting a warm, chemically active ocean below its icy crust. Titan, with its thick atmosphere and liquid methane lakes, offers a completely different kind of chemistry, one based on hydrocarbons rather than water. Life on Titan, if it exists, would be unlike anything we know, adapted to extreme cold and using methane as a solvent instead of water. All three moons have the basic ingredients for life: liquid, organic molecules and energy sources. Upcoming missions like NASA's Europa Clipper and the Dragonfly mission to Titan will search for signs of life or conditions that could support it. These moons represent our best chance of finding life within our own solar system. And as we search for life, certain chemical signatures become important. Oxygen in an atmosphere isn't always a sign of life. It can form through other processes. On Earth, the vast majority of atmospheric oxygen is produced by photosynthetic organisms, so finding oxygen on an exoplanet is considered a potential biosignature. However, oxygen can also be produced abiotically without life. For example, ultraviolet light from a star can split water molecules into hydrogen and oxygen, with the lightweight hydrogen escaping into space and oxygen accumulating in the atmosphere. This process is thought to have occurred on Venus and Mars. Similarly, oxygen can be produced by the photodissociation of carbon dioxide or by geological processes. Finding oxygen alone is not enough to confirm life. Scientists look for combinations of gases that are unlikely to coexist without biological activity, such as oxygen and methane together, which would react and disappear unless they're being continuously replenished. And detecting multiple biosignatures strengthens the case. The presence of multiple biosignature gases together is more compelling than one alone. A biosignature is a chemical or feature that indicates the presence of life. On Earth, our atmosphere contains oxygen, methane, water vapor, and other gases in proportions that are maintained by biological activity. If we detect a similar combination on an exoplanet, especially gases that would normally react with each other and disappear, it suggests something is actively replenishing them, possibly life. For example, finding both oxygen and methane in an exoplanet's atmosphere would be intriguing because these gases react to form carbon dioxide and water. Their coexistence would require a continuous source, which on Earth is provided by life. Similarly, finding phosphine, a gas produced by some microbes along with other biosignatures, would strengthen the case for life. No single gas is definitive proof of life, but a combination of gases in unusual proportions, especially if they persist over time, is a strong indicator. And even in our own solar system, there are places where life might exist in surprising forms. Some scientists believe life could exist in the clouds of Venus. Venus's surface is a hellish environment, with temperatures hot enough to melt lead and atmospheric pressure 90 times greater than Earth's. However, high in Venus's atmosphere, about 30 to 40 miles above the surface, conditions are much more temperate. Temperatures are around 85 degrees Fahrenheit, and the pressure is similar to Earth's at sea level. This region of the atmosphere could potentially support microbial life, floating in droplets of sulfuric acid and drawing energy from sunlight. In 2020, scientists detected phosphine gas in Venus's atmosphere, a gas that on Earth is primarily produced by anaerobic bacteria. While the detection and interpretation of the phosphine signal remain controversial, it sparked renewed interest in the possibility of life on Venus. Upcoming missions to Venus will search for more evidence, studying the atmosphere in detail and looking for other biosignatures. If life exists on Venus, it would be a form of extremophile, adapted to the acidic, high-altitude environment. And beyond planets, their moons might also be habitable. Exomoons, moons orbiting exoplanets, could potentially be habitable, just as our own solar system has moons with subsurface oceans and intriguing chemistry. Exomoons around gas giants in the habitable zones of other stars could be warm, wet, and capable of supporting life. An exomoon could be heated by tidal forces from its parent planet, keeping it geologically active and maintaining liquid water beneath an icy shell similar to Europa. Alternatively, an exomoon orbiting in a star's habitable zone could have surface oceans and Earth-like conditions. Detecting exomoons is challenging because they're much smaller than planets and their signals are faint, but astronomers are developing techniques to find them. If large exomoons exist around gas giants in habitable zones, they could significantly increase the number of potentially habitable worlds. And some stars offer especially long timescales for life to evolve. Planets around red dwarf stars could remain habitable for trillions of years. Red dwarfs are the smallest, coolest, and longest-lived stars, burning their fuel so slowly that they can remain stable for 10 trillion years or more, hundreds of times longer than the Sun's lifespan. This gives life on planets around red dwarfs an enormous amount of time to evolve, adapt, and potentially become complex. Even if conditions on these planets are initially hostile, with strong stellar flares and tidal locking, life might find a way over billions of years. The long lifespans of red dwarfs mean that planets in their habitable zones will remain warm for much longer than Earth will, long after our Sun has become a red giant and sterilized the inner solar system. If life is common in the universe, red dwarf systems may ultimately be where most of it exists, simply because these stars provide stable environments for such vast stretches of time. And as we look to the future, new missions will help us explore these possibilities. NASA's mission to Europa will search for signs of life beneath its icy surface. The Europa Clipper mission, set to launch in the 2020s, will orbit Jupiter and make dozens of close flybys of Europa, studying its ice shell, subsurface ocean, and geology. The spacecraft will carry instruments to measure the thickness of the ice, analyze the composition of surface materials, and search for plumes of water vapor erupting from the surface, similar to those on Enceladus. If plumes are found, the spacecraft could fly through them and sample the ocean material directly. Europa Clipper will also study Europa's magnetic field and gravitational field to confirm the presence of the subsurface ocean and estimate its depth. The mission won't land on Europa, but it will provide critical data for future missions that might drill through the ice and explore the ocean below. Europa is one of the most promising places in the solar system to find life, and this mission is a major step toward answering that question. And beyond Europa, other missions are exploring distant worlds. The Nancy Grace Roman Space Telescope will directly image exoplanets and study their atmospheres. Scheduled to launch in the mid-2020s, the Roman telescope will use a coronagraph to block out the light from stars, allowing it to directly observe planets orbiting nearby. This technique will enable scientists to take spectra of exoplanet atmospheres, identifying the gases present and searching for biosignatures. Roman will focus on gas giants first, as they're easier to image, but future upgrades or follow-on missions could extend its capabilities to smaller, Earth-like planets. The telescope will also conduct surveys to find thousands of new exoplanets using gravitational microlensing, a technique that detects planets by observing the way their gravity bends light from background stars. Roman will complement the James Webb Space Telescope, providing a new perspective on exoplanets and advancing our understanding of planetary systems. And closer to home, Titan is the target of another ambitious mission. Dragonfly mission will fly through Titan's atmosphere and land in multiple locations. This quadcopter-style drone will explore Saturn's largest moon, studying its surface, atmosphere, and chemistry. Titan's thick atmosphere and low gravity make it an ideal place for aerial exploration, and Dragonfly will take advantage of this by flying between different sites, covering hundreds of miles during its mission. The drone will search for signs of prebiotic chemistry, the organic molecules and reactions that could lead to life. It will also study Titan's methane cycle, exploring lakes, dunes, and impact craters. Dragonfly is scheduled to arrive at Titan in the mid-2030s, and it represents a new era of planetary exploration. using advanced robotics to access environments that would be difficult or impossible to reach with traditional landers or rovers. Titan's Earth-like processes, despite its alien chemistry, make it one of the most fascinating destinations in the solar system. And even more ambitious projects aim to reach the stars themselves. Breakthrough Starshot aims to send tiny probes to Proxima Centauri within our lifetimes. This ambitious project proposes using powerful lasers to accelerate tiny spacecraft, each weighing just a few grams, to about 20% the speed of light. At that speed, the probes could reach Proxima Centauri, the closest star system to Earth, in about 20 years. The probes would carry cameras and sensors, capturing images and data as they fly through the Alpha Centauri system, including Proxima Centauri b, the nearest known exoplanet. The data would be transmitted back to Earth, taking another 4 years to arrive. The technology required for Breakthrough Starshot is still being developed, including the laser array, the light sail propulsion system, and the miniaturized instruments. If successful, the project would mark humanity's first journey to another star system, a monumental achievement. And in the coming years, closer to home, we may make another historic discovery. Within the next decade, we may find the first strong evidence of life beyond Earth. With missions like Europa Clipper, Dragonfly, and the James Webb Space Telescope actively searching for biosignatures, we're closer than ever to answering one of humanity's oldest questions. Are we alone? The discovery could come from detecting gases like oxygen and methane together in an exoplanet's atmosphere, finding organic molecules in the plumes of Enceladus, or discovering microbial life beneath the ice of Europa. It might not be the dramatic encounter with intelligent aliens that science fiction imagines, but the discovery of even simple, single-celled organisms would be profound. It would tell us that life is not unique to Earth, that the processes that led to biology here can happen elsewhere. It would change our understanding of our place in the universe, transforming Earth from the only known cradle of life into one of many. And as we continue to explore, as telescopes grow more powerful and spacecraft venture farther, the answer grows closer. We stand on the threshold of discovery, looking up at the stars with new eyes, new tools, and new hope. And now, our journey through 100 planetary facts comes to a gentle close. As you lie here now, your body still and your thoughts drifting, remember that planets are turning. Right now, at this very moment, distant worlds are spinning through space, orbiting stars we'll never see, carrying secrets we may never know. But we're looking, we're listening, and with every passing year, we learn a little more. If your eyes are heavy, if sleep is pulling you gently down, let it come. There's no need to hold on. The planets will still be there in the morning, circling their stars, waiting patiently in the quiet. And if you'd like to return to these stories another night, you're always welcome here. Thank you for sharing this journey. Rest well, dream of distant skies, and good night.